Unit 7, pages 225 to 227. Volumes of solids of revolution. A solid of revolution is formed when a flat, two-dimensional shape is rotated around an axis. Consider the flat region below to the left. When that region is rotated about the x-axis, the solid pictured below to the right is formed. This objective of this lesson is to learn to find the volume of such a solid. So now imagine slicing a solid into individual disks of height 1 unit. The volume of one of those disks is V equals pi r squared h, or V equals pi r squared, since h is 1. So if this is my two-dimensional figure, and then I take that figure and I rotate it over the x-axis, this is the figure that it creates. So all this area in here is getting rotated around the x-axis. So this is a solid figure. There's no holes in it. It's a solid figure because all the area is rotated around the x-axis. So if I were to slice open this figure, right? So here's the slice that I'm going to cut out. If I were to slice that figure out, I would get, probably doesn't look as nice, but I would get something that looks something like this. Okay, and that's if I rotate it around and then place it on the desk. If not, then I get this figure right here. Okay, so I've taken this figure and I've placed it on the desk. So the height of this figure is x. Okay, so this height is x. The middle of this figure is my axis. So right in the middle of this is my x-axis, because that's what I'm rotating it over. And then if I look here, the length of this is just whatever f of x is at that x value. So this is f of x to my x-axis. And if you look closely, this length is my radius. Right? And then the other side is the same, it's the axis, and then f of x down at the bottom. Okay, so the length of x is going to be some value from A to B. So knowing that information, knowing that the volume of a cylinder like that is pi r squared h, where h is 1 unit, so we're saying that x is just 1 unit. We don't know how long that 1 unit is. It's just 1 unit in our case. So if I add up all of those cylinders, then I get the definite integral from A to B, whatever value A to B is. In this case, we're going to go from A being over here to B being over here. And this is just little a and b's, but our large a and b is the entire limit we're looking at. So we need pi on the radius. So this here is our radius, right? F of x minus our axis of rotation, and in this case it's the x-axis, squared dx. So when we add up all of these cylinders, we're actually just getting the volume of the entire solid. So the volume of the solid is pi times the definite integral from A to B of f of x minus the axis of rotation squared dx. Okay, so notice that the axis of rotation is the x-axis And the bottom function of the region is also the x-axis. So by bottom function, what I mean is this function, right? We have f of x up here, and then the second function that we're looking at is the x-axis. We're taking the area between the function and the x-axis, and then we're rotating that function. So that bottom function is wherever our line is for if there's a second function. Wherever that is, that's our bottom function. So imagine for a moment what the solid would look like if the axis of rotation was still the x-axis, but the bottom function of the region was the line y equals c. The solid would look similar except for the fact that there would be a cylinder that is cut out of the center. So an example of that is down here. So we still have f of x, but now our bottom function is y equals c. So we're taking the area between our function and y equals c, and then we're going to rotate that over the x-axis. So that leaves us with is this open space between c and the x-axis. Right, so if I were to again draw a cylinder that represented this, really bad drawing skills, but if I were to draw a cylinder that represented the situation, it would be way larger than that. So I'm just going to draw a smaller cylinder that would be over here. Right, so then in the center of that cylinder, that open space will create a hole. Right, so this was open space. That open space creates a hole in our cylinder. So instead of having a regular cylinder, now we have what some people call a washer. Okay, so above we had a disc, and now we have a washer. Right, a washer has this open space in the center. So in order to figure out how to find the volume of that, now we're looking at the space from f of x to our axis, right? In this case, it's y equals c. And then we're going to subtract that from the space from our axis to our x-axis. Right? So we're starting with f of x to our axis. So f of x to the y-axis, and then we're going to subtract from it the space in between from our inner function, which was y equals c, minus our x. Okay, so the outer function is defined to be the function that is farthest from the axis of rotation. So we are spinning this around our axis of rotation. And in this case, our axis of rotation is the x-axis. So the function farthest from the axis of rotation is my f of x function. The inner function is the function closest to my axis of rotation. So that was our y equals c. So our outer is f of x in this case, and our inner was y equals c in this case. So to find the volume in a situation like that, we have pi, definitely going to go from A to B, of f of x minus 0, because our axis of rotation is the x-axis, squared minus c, because that's our inner function, minus our axis of rotation, 0, squared dx. if the axis of rotation is the x-axis or is parallel to the x-axis, so that means that it's y equals some number, then the integrand needs to be in terms of x and the limit of integration needs to be x values from the point of intersection of the curves that form the region being rotated. So we have the graph y equals x squared and y equals x plus 2. So here's x squared, here's x plus 2. We need to find the volume of the solid formed when the region is rotated about the x-axis. So the x-axis is when y equals 0, and that's our axis of rotation. So we need a few things before we can figure this out. First thing that we need are the points of intersection, because our points of intersection are going to give us the limits of integration. So our points of intersection need to be, as it says here, the x values from the points of intersection are going to be our limits of integration. Our limits of integration are -1 and 2, right? The x values from our points of integration. So we're going to do the volume equals pi from -1 to 2 of, we need the upper function, right? So this comes from our video from last night where we're looking at the area between two curves, right? So the upper function is our x plus 2. And we're going to subtract from that our axis of integration, our axis of rotation, sorry. Our axis of rotation is y equals 0. We're going to subtract from that 0 squared. Now, we're going to subtract our inner function squared minus our axis of rotation, which is 0 squared dx. So this is a situation where we're going to take this space and we're going to rotate it. So all this empty space needs to not be included because all we're rotating is the area between these two curves. Okay, so then v equals times definite interval of x squared plus 4 minus to the fourth. All I did was square these two sections. Dx. Now we can actually integrate. So v equals pi times 1/3 x cubed plus 2 x squared plus 4x minus 1/5 x to the 5th from -1 to 2. So v is equal to pi times 8/3 plus 48/3 minus 32 minus -1/3 minus 6/3 plus 1/5. So v equals pi times 21 minus 33/5. V equals pi times 1/5 minus 33/5. V is equal to 72/5 pi. That would be the volume of the solid created from taking this area and rotating it about the x-axis. Okay, so now We're going to find the volume when the region is rotated about the line y equals 4. So now we're going to rotate this area about the line y equals 4. Okay, so here our inner and outer functions are different, right? Our inner function now is the function closest to my axis of symmetry. So that would be the x plus 2 function, and our outer function is x squared because that's the curve farthest from our axis of symmetry. So when we write our equation, we have equals I. Still the same limits of integration, -1 to 2 of our outer function, which is x squared, minus our axis of symmetry, which is 4 squared, minus our inner function, 2, minus our axis of symmetry, which is 4 squared dx. So then v equals pi times definite interval from -1 to 2, x to the 4th minus 8x squared 16 minus x squared 4x minus 4 dx. So combining those terms, we get pi times the interval from -1 to 2 of x to the 4th minus x squared plus 4x plus 12 dx. And after we integrate, we get pi times 1 over 5x fifth minus 3x cubed plus 2x squared plus 12x -1, 2 is equal to pi times 32 over 5 minus 24 plus 24 plus 8 minus -1 plus 3 plus 2 minus 12 pi times 33 over 5 which is equal to 184 pi. Okay, so the trick here is visualizing where your axis of symmetry is so that you can identify the inner and the outer functions to write your volume equation. Okay, so in this case, we want to find the volume when the region is rotated about the line y equals -2. So now we're rotating along the line y equals -2. So now my inner function is x squared because that's the line closest to my axis of symmetry. And then my outer function is x plus 2 because that's the line farthest from my axis of symmetry. So I want you to set up and complete this problem on your own and identify what the volume would be if we rotate the line if we rotate our area about the line y equals -2. Okay, so now we're going to look at a similar problem where the axis of symmetry is now the y-axis and not the x-axis. So if the axis of symmetry is the y-axis or is parallel to the y-axis, so if our function is in the, if a function looks like x equals some number, then the integrand needs to be in terms of y and the limits of integration need to be y values from the points of intersection. So we're going to consider the region pictured to the right that is bounded by the graphs y equals positive negative square root of x and y equals x minus 2. So because we're going to be rotating about the y-axis, there's a few things that we also need to do. We need to rewrite this equation, or both of these equations, so that they are in terms of x equals, not y equals. So we're actually going to solve these equations for x. So if I square both sides, I get y squared equals x. And if I add 2 to both sides here, I get y plus 2 equals x. So these are going to be the equations that we use because we need our equations to be in terms of y. So to find the volume when the region is rotated on the y-axis being there, we need the volume equation, so v equals pi times, now we need the limits of integration. So our limits of integration come from our points of intersection, and they come from the y value of those points of intersection. So my limits of integration are -1 and 2. So from -1 to 2. And since we're rotating about the y-axis, we're looking at which equation is closest to the y-axis, that will be my inner, and which equation is farthest away, that will be my outer. So the equation that creates this curve is my x equals y squared equation. The equation that creates this line is my x equals y plus 2 equation. So the farthest equation, my outer function, is my y plus 2. So I'm going to have y plus 2 minus my axis of symmetry, which is 0, squared minus my inner function, which is y squared, minus my axis of symmetry, which is 0, squared dx. Oh, actually dy, since we're in terms of y. So then v equals pi, definite integral from -1 to 2 of y squared plus 4y 4 minus y to the fourth dy. So v equals pi times 1/3 y cubed plus 2y plus 4y plus 2y squared plus 4y minus 1/5y to the fifth from -1 to 2. And even though the letters are different, this is the same equation that we looked at on the previous page. So it'll still give us the same value when we put in -1 and the 2. So v is equal to 75 pi. So for the second problem, we want to find the volume when the region is rotated about the line x equals 4. So now we're saying we're looking at the line x equals 4. So we're looking at this vertical line, and we're going to rotate this area about that line. So the function farthest away, my outer function from this line, is going to be my y squared function, and the function closest, my inner function, will be y plus 2. So when I set this up, I get v equals, then same limits of integration of y squared minus 4 minus y plus 2 minus 4 squared dy. The reason why we put 4 is because 4 is my new axis of symmetry. Okay, and if you look at our previous page, this is the same setup as before, except instead of x, we have y. However, we get the value 108 over 5. Okay. This last problem wants us to rotate about the line x equals 7. So now we're going to be way back here, x equals 7. So our inner and outer functions are still going to be the same as they were for equals 4 because we're still rotating the same area about now a new axis of symmetry of rotation, which is going to be x equals 7. So we have v equals definite interval from -1 to 2 of my outer function, which is y squared, minus my axis of rotation, which is 7 squared, minus my inner function, which is y plus 2, minus my axis of rotation, which is 7 squared dy. So v will be equal to pi times -1 to 2 of y to the 4th minus 14y squared plus 49 minus y squared plus 10y minus 25 dy. When we simplify, we have v equals pi and 7 goes from -1 to 2 y to the 4th minus 15y squared 10y plus 24 dy. So v is equal to pi times 1/5 y to the 5th minus 15 over 3 is 5. So 5y cubed plus 5y squared plus 24y from -1 to 2. So v is equal to pi times 32 over 5 minus 40 plus 20 plus 48 minus -1/5 plus 5 plus 5 minus 24. Okay, so then v is equal to pi times 33 over 5 plus 42, which is equal to 243 over 5 pi. Okay, this is a lot of information. Volumes of solids of rotation it can be very complicated. We will be doing a little bit more practice, especially when it comes to review before the exam. Please, please, please do your best that you can on those homework assignments and ask questions if you need help, because those homework problems are crucial to really understanding how to do these types of problems, and also very helpful in the next video that we're going to do.